Okay, welcome to another Stat 432 video. We're going to pick up kind of where we left off with logistic regression, but now not talking about logistic regression, but binary classification. So everything we see in this video will apply to logistic regression, but also to k-nearest neighbors if you only have a binary outcome, or say a decision tree model if you only have a binary outcome. So what we have here is some data that I made up. So the actual data, oh boy. So the actual data is the yi's, and this could be either in the validation set or the test set. More on that in a second. And then the predicted, in this case, would be, we trained some classifier and we got the output of it. And here's what we get, right? So we have actual zeros and ones and predicted zeros and ones. And again, remember that in binary classification, we often call the 1 the positive class and 0 the negative class. Okay, so now we want to make this thing called a confusion matrix, which just counts up how often is the actual what is predicted. So let's see, a few things here. It looks like we have here, here, and here. So that's 1, 2, 3 actual ones that are predicted ones. Here we have an actual 1 that is predicted 0, and there's just one of those. Here we have a couple true zeros that are predicted 1. And then lastly, we have here, 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 and here, actual zeros that are predicted 0. So 1, 2, 3, 4 of those. Okay. And just note, so the way I made this confusion matrix, I have the actual on the top and the predicted on the left. That's arbitrary. Different software packages will flip those. You could also flip the placement of the 0 and 1. It's most important to know that, like, okay, well, here's actual, here's predicted, here's 1, there's 3 of them. So knowing what the individual cells are and the numbers that are in those cells are the important thing. And then also note, up top here, I just have this mentioned that this confusion matrix could be for the validation data, like we could evaluate how well our classifier is working based on this confusion matrix and some metrics we're about to see. So we fit the model to estimation, make the predictions on the validation, and evaluate the confusion matrix. Or we could look at the confusion matrix as sort of a more reporting thing. That is, we already validated and picked a model, so then we refit it to the whole training data, and then we then compute the confusion matrix on the test data. Okay, so this is just recapping what I had said a second ago, but now instead of tallies, I have numbers. So first note that we often refer to the minority class and the majority class. So I already did some tabulation here. So there were 4 positives, which in this case are the minority class, and there were 6 negatives, which in this case are the majority class. So now what I want to do is define what each of these cells means. And these are some terms that hopefully you've run into before, but if not, they're not too hard to pick up. So this example here, it's actually a 0 and it's predicted a 0. That's what we would call a true negative. And let's see, there were 4 of those and they were here. So these are the true negatives. So those are not errors. They are negatives and we predict them negative. That's good. The other way we can be correct is down here as an example of it. This is a true positive. That is, it's actually a positive and we predict it as such. We had 3 of those that were right here. Those are the true positives. Then there were 2 types of errors we can make. The first one we see here. So it's actually a negative, but we predicted a positive. So that is what we would call a false positive. And we had a couple of those, and on the confusion matrix they are here. False positive. And then the other error we could make is it's actually a positive, but we predict it to be a negative. So that would be a false negative. And those are here. So you have the 2 ways of being correct and the 2 ways of being incorrect. And depending on the context of the problem, which is, maybe you're detecting whether or not someone has cancer, maybe you're detecting whether or not someone fails or passes a class, and depending on even just which class you define to be the minority, or sorry, the positive or the negative, you might care more about false positives or false negatives. So we can develop some metrics that instead of only looking at the accuracy of a classifier, they will be more weighted towards either a false positive or a false negative. Okay, so this is the slide where I say that based on the confusion matrix, which I've repeated here, there are a large number of metrics that we could calculate. And I have this note here in the bottom left that says there's a lot more. And I'm going to link to a Wikipedia article on the confusion matrix where it just has a gigantic list of different metrics that you could calculate. And it's not even super important that you remember off the top of your head what each of these metrics is. What's more important that is if I give you the definitions in terms of false positives, false negatives, true positive, true negatives, then you can sort of derive some meaning from it. But we'll start with accuracy, which is something we've already seen. But now in terms of these new things we've defined, well, the accuracy is the true positive plus the true negatives, in other words, the diagonal there, divided by the total number of observations, which it could also be the positives plus the negatives. So we have, so that means we have, let's see, there were 3 true positives plus 4 true negatives divided by 4 positive plus 6 negatives for a 0.7 accuracy. And I'd also note that the accuracy is 1 minus the misclassification rate. Sometimes we talk about misclassification, sometimes we talk about accuracy. Sort of depends on context, but just know that those are sort of interchangeable. Either you want a model with high accuracy or low misclassification, but they're just 1 minus each other. Okay, so now calculating a few more metrics here. So the first one is the prevalence, and the prevalence is just, well, how often does the positive class appear? So in this case, that is 4 divided by 4 plus 6 for 0.4. This is something you should always look at for any classifier, and we'll see why on the next slide. So the next two are two metrics that are probably the most important after accuracy, which are sensitivity and specificity. If you've ever sort of discussed like medical diagnostic testing before, these two come up a lot. So the sensitivity is of the things that are truly positive, how many did we identify? So that is the true positives divided by the number of positives, which is here 3 divided by 4, so 0.75. So this is essentially the rate at which we're detecting the positive classes. So on the other side of this, we could look at the specificity, which is of the things that are truly negative. So you could sort of think about that as, we're conditioning on being within this column now. How many of them did we identify correctly? That is, how many did we label as negative? So in this case, we would have 4 over 6 for 0.666 repeating, of course. So those would be sort of important things. So like if you know that detecting all the positives are is a really good thing. So like say, I guess to date this video, if you were developing a test for COVID-19, you would want a really high sensitivity because if it doesn't have a high sensitivity, well then some people with the disease will not be tested. They will not have a positive test, and then they'll be released back out into the population and possibly infecting more individuals. Now that comes with a trade-off, which we'll talk about on a later slide. Basically, to increase the sensitivity of a classifier, you often decrease the specificity. So in the example I just said, the medical testing versus classifier is confusing this, but if we create a classifier that's highly sensitive, that means so if someone has the virus, we detect it. Well, that comes generally at the cost of increased false negatives. False negatives. I confused myself. We're going to correct that on the next slide. I shouldn't be doing this out loud. I need to do it with a concrete example. We'll see on the next slide. Anyway, so these next two metrics, positive predictive value and false discovery rate, they're actually not going to be things we talk about all that much in this class, but I just wanted to say like, hey, look, as long as I give it to you defined in terms of the four possible outcomes, true positive, false negative, false positive, true negative, you can calculate these things. And then I think we can reverse engineer the meaning a little bit here. So I think there's 3 true positives divided by 3 true positives plus 2 false positives, right? That gives us a 0.6. So here we're looking at essentially conditioning on this row. So it's of the things that we predicted to be positive, how many of them were truly positive? And then the false discovery rate is sort of similar. It's still conditioned on that same row, but now we're saying, well, how often are we labeling something as positive that shouldn't be? So this is 2 plus 3. Again, the context of these is all dependent on the problem and how you define things to be positive. We will probably have you calculate some sort of what we'll call like lesser used metrics, but we're not going to expect you to have their definitions memorized. We're debating whether or not you have to memorize sensitivity and specificity, but it's more important that you can calculate these things given the definition, but you will need to know what is a true positive, what is a false positive, what is a true negative, what is a false negative. That we think is something that you should have memorized. Because if you have that, everything else follows from. Okay, so I mentioned that this prevalence is something that you should always calculate for the data sets that you're, because essentially they don't actually care about what you're predicting, because you only care about the number of positive and the number of negative. So you should always calculate this in your validation set if you're validating based on these metrics, or in your test set if you're reporting based on them, for the following reason. We need to talk about something called the no information rate, which it turns out it's just the proportion of majority of the majority class. So here is the prevalence, which is the proportion of the positive class. And then here is 1 minus the prevalence, which is the proportion of the negative class. And whichever one of those is bigger, so whichever one is the bigger proportion, is what we call the no information rate. And this is important because if your accuracy is above your no information rate, that's what I'll call a reasonable classifier. But if your accuracy is less than the no information rate, that's no good. That's not a good classifier, because essentially what that's saying is that if instead of using the classifier you just developed, if I just always predicted the majority class, I would be doing better. So if we look back here, our accuracy was 0. Let's see here. Our accuracy was 0.7 with this little thing I developed, and our prevalence was 0.4. So that would mean 0.4 here and 0.6 here, the max of which is 0.6. Okay, so our accuracy was bigger than our no information rate, so that classifier that I made up was reasonable. Okay. Okay, so going back to binary classification for a moment, we sort of defined this quick notation. If we say y is 0 and 1, again, 0 and 1 being placeholders for, pass, fail, dog, cat. This p of x is the probability that y equals 1 given x equals x. So then if we knew those probabilities, didn't have to estimate them, the Bayes classifier would be like this, where we classify to 1 if the probability that y equals 1 is greater than 0.5. Well, why is that? Well, that's exactly because the probability that y equals 1 given x is x is then greater than or equal to the probability that y equals 0 given x equals x. So that's just sort of natural. You're classifying to the majority class. This equals is sort of arbitrary. You could put it almost on either side. You could also flip a coin there, but we're going to sort of just define it this way for simplicity. Okay, so, but this is, this is the Bayes classifier. We wouldn't know this. What we'd actually have to do in practice is estimate this quantity. Okay, so let's say we did that. So first of all, how do we estimate this P of X? Well, you can do it with KNN, tree, logistic. We'll talk about something called naive Bayes. But ultimately, all these things, you fit them in R, you use the predict function, and it'll output the thing you care about, which is the estimated probability that Y is 1, given whatever observation you input. Okay, so I'm going to define a classifier as something that is based on that estimated conditional distribution of Y given X, but also now a cutoff. And I'm going to call that cutoff, I guess my better judgment, I'm going to call it alpha, even though alpha is often defined as other things. But so I'm going to use this notation C of alpha of X to determine a classifier. And so alpha determines the probability at which you classify to 1. And unless we specify a different alpha, we assume that it's 0.5, which is, sort of how the Bayes classifier would work to maximize the accuracy or minimize the misclassification. But we set alpha to be modifiable because, as you increase alpha, it is harder to classify to Y equals 1. And so if we sort of think about that, if we make it harder to classify as 1, you'll sort of reduce true positives, but you'll also reduce false positives, right? So that'll have an effect on sensitivity and specificity, and that's what we're going to look at in a second. But basically, a classifier, so what we're saying here is that a classifier is a function of two things. Doing the, that looks like a beta, that's no good. Doing the estimation of the conditional distribution of Y given X and some cutoff. And, most of the time we'll use a cutoff of 0.5, but now we're going to demonstrate how modifying that cutoff works. Okay, so bear with me on this slide. So what do we have here? So first, this column is the actual values of Y. And now instead of the predicted values, I have for each observation the estimated probability that Y is 1 given the X value, which we haven't even seen. Okay, and then so what I have here is what we were previously calling the predicted values, which is, using a cutoff of 0.5. So I have that 0.5 here. And we see that, 0.1, 0.1, 0.2, 0.3, those are all less than 0.5. So we get these zeros here. And then for the rest are 1 because these are all above 0.5. Okay, great. And then we see the sensitivity, specificity, and accuracy that we saw before. Is that right? Yeah. Okay, cool. All right, so then what I did is I have 4 more columns for 4 different classifiers. They're all using the same estimated probabilities, but now with different cutoffs. So if we go to the 2 extremes, so first a cutoff of 0, well, that means that any observation is going to be classified to 1, because if we put 0 here, well, probabilities are only between 0 and 1. We're classifying everything to 1. So our accuracy goes way down because we only get these observations correct now. Our specificity absolutely tanks, but now our sensitivity is through the roof because, well, here are the positive values, and then these are all true positives, so 4 over 4, there we go, that's wonderful. Now on the other end of things, if we go to an alpha of 1, that means we're effectively classifying almost nothing unless we know for a fact it has a probability of 1 as Y equals 1. So our sensitivity tanks now because we misclassify all of the 1s, but our specificity is now perfect, and our accuracy, we got these right and these wrong, so 60%. What happens in the middle? So if we have this 0.25 here as a cutoff, So now I'm going to make the classification. So that's a 0, that's a 0, that's a 0, and then we get to this 0.3, so that's a 1, and everything else will be a 1 because I think those are all bigger. Okay, so then for the sensitivity, I need to look at these observations here. So within those, how many did we label as positive? Well, all of them. So we still have 100% here, but then our specificity within these, we label these as 0, so that looks like a 0.5. And our accuracy, let's see, I said these are correct and these are correct, so that looks like 0.7. I did that kind of fast, but if you go back to the previous definitions, that shouldn't be too hard to do. And then if we do sort of something else in between, a 0.75 here, so that means this would be classified to 1, this would be classified to 1, and I think the remainder here are all less than 0.75. So you get something like that. Okay, so our sensitivity within the ones here again, we get these 2, so that's 50%. Within the zeros, we get all of them. That looks good, so we get 1 here. And then that's 1, 2, 3, 4, 5. So an 80% accuracy. Okay, cool. So this maybe isn't the best illustration, but you can kind of see something here. Excuse me, I'm talking too much. As the alpha decreases, the sensitivity goes up. And that just sort of makes sense, right? Because the sensitivity is, well, how many of the things that are truly positive are we labeling as positive? And well, if you decrease alpha, it makes it easier to classify to the positive class, so it goes up. Specificity has the opposite relationship. As you increase the cutoff, specificity goes up, because as you increase the cutoff, you're predicting more things to be negative. So obviously, of the things that are truly negative, you will label more of them correctly. And then, so this example isn't the best because generally you would expect a cutoff of 0.5 to produce roughly the best accuracy. And then the further you move away from that, it decreases. You sort of see that on this side, and it is lower here, but just due to the random chance of this, so let's call it test set, we get a higher accuracy here. But generally, you expect it to be the highest at 0.5 and then decrease as you move further away. So then just one more quick note. We can talk about evaluating our estimated probability distribution instead of the classifier using something called an ROC curve. So the ROC curve sort of takes two things as input. The estimated probabilities that y is 1 for each observation, and the true labels of 0 or 1, and then it creates a plot like this, where on the y-axis we have the sensitivity going from 0 to 1, and on the x-axis we have the specificity going from 1 to 0. So what the gray line here is a line for what we would call guessing. So that's sort of like the barrier. You got to get above that. That is guessing based on the proportion of the positives and negatives. But anyway, so then what we have plotted here is, well, what would be the resulting sensitivity and specificity if we used this estimated distribution with a cutoff of 0.1, well, and that would relate to a specificity of 1 and a sensitivity of 0. And then up here, we have, well, if we have an alpha of 0, well, then specificity 0 and sensitivity is 1. And then sort of, in practice, this won't often be a nice curve. It'll be a little bit more jagged. But imagine starting with alpha 0 and decreasing it, sort of like sweeping all the way to 0, and then we plot those sensitivity and specificities. And that we want is this curve to push as close to this point here, which would be sort of like the perfect classifier where you have a specificity of 1 and a sensitivity of 1. And so the way we measure how good this distribution is with something called area under the curve. So you could, like an R package will give you that area under the curve, and the bigger is better. If it's 1, it's perfect. If it's 0.5, which is what this curve gives you here, that's sort of no better than just guessing based on the response. Okay. We might come back to ROC curves a little bit later, but we'll maybe circle back to them when we start using R packages that sort of make it easy to do them. But for now, we're going to focus on sort of calculating these metrics. And one thing I'll say here is that there are a lot of R packages that'll just calculate these for you. And we'll go there eventually. But the thing I want to say is those packages often can be tricky because you have to pay a ton of attention to, well, what is the positive class? What is the negative class? How is that being defined? Like sometimes it's automatic. What I would say is I think it's important to, given an actual vector and a predicted vector in R, being able to calculate these four cells. And then once you do have that, these are all trivial. So it's my strong suggestion that at least for a little while until we get to the end of the semester, when we do things more quote unquote practically, I would focus on being able to calculate true positives, false negatives, true negatives, and false positives sort of with your own functions in your own R code, and wait to use a package later on. Okay, so again, and this slide is a huge mess right now. The version I'm posting will have better handwriting, so do look for that. And as always, I have no idea how to end these videos other than to say, if you made it to the end, good job.